This is Professor Amiya Kumar Sharkar giving you a very brief video presentation on error control codes. My dear students, we have already covered block codes, code words, information vector, parity bits deriving equations, systematic and non-systematic block codes, weight of a code word, WC, distance between two code words, that is D within bracket CI comma CJ bracket close, minimum distance D min of a block code. We will in this very small video presentation now focus on computation of the code word for a given information word and a set of parity bits deriving equations. Then we will compute WCs applying the given set of parity deriving equations, and thereby we will obtain DC1 C2 for two code words C1 and C2. The next exercise we will see how to obtain D min, and the critical computation issues of D min will be discussed. Then we will come to what happens for a block code with reference to evaluation of D min. Then it will be followed by a discussion, very brief discussion rather, on what is a linear block code, what are its features, how easy is now the computation of D min, you will see. Then we will discuss the error detecting and correcting potentials of linear block codes and the implication of the minimum distance D min in obtaining these values. After the completion of this very little journey on discussion of block codes and related computations, we will do the following exercises. We will first do some PI exercises in the class, then one or two think pair set exercises. Finally, I will give you some quiz questions and one or two lengthy homeworks for C-based program development for some of the computations that you do manually. Fine. Now let us proceed and see what next. This subject is information theory and coding, and the topic is block codes, where we will deal with code word formation, calculation of code weight, code distance and minimum distance, as I said. This has been assisted by Mrs. Pranati Datta, one of the faculty member from the EI department throughout, and I am really grateful towards her for helping me out throughout the entire process. We now proceed to the computation of code words for a given information word and a set of parity weights deriving equations. Let us take, for example, a 7-4 block code where parity check bit can be derived, for example, from the following equations. Equation 1 is for the parity check bit 1. This is the equation. Equation 2 is for the parity check bit 2, P2, that is I1 plus I3. Information bit 1 and information bit 3 is modulo 2 added to produce this parity bit. Then the equation 3 gives you how you form the parity bit 3, P3, this one. And I2, I3 and I4 are added by modulo 2 operations to obtain the information bit 3. Next we observe what happens for a code word, for a information word rather, or information vector 1001. Here we evaluate from the above set of equations. The value of P1 is 1, that of P2 is also 1, that of P3 is also 1, and the code word finally becomes 1001111. This is a systematic code for which the code word is obtained as follows, where information vector I is followed by the parity vector p. Okay, and the another code word C2 is also formed by using the information vector I21110, and the code vector here is C2 1110,000. If you compute, you will find the following code word being generated. Okay, next we proceed to the computation of weights of the two code words C1 and C2 that we have already obtained. Weight means what we have already discussed previously. It is the number of ones that is present in the corresponding code word. That is, in case of C1, it is WC1 equals to 5, because 5 ones are out there. If you see, if you go back and observe, you will find 5 ones are there in the code word. And in case of WC2, it is 3, because 3 ones are there. When you evaluate the value of DC1 C2, that is the distance between these two code words, okay, C1 and C2, you obtain DC1 C2 is 6, because they to differ in the 6 different bit positions, and you just don't calculate by subtracting the weight values, that is WC1 minus WC2, to obtain the value 2. Here you should not be confused, as I already have discussed in the class. Fine. Next, obtaining the d-min. The interesting feature is in case of a nonlinear block code, it's very difficult, as we will see, to obtain the value of d-min by computation. This is the critical aspect of computational issues that we must notice. In case of a nonlinear block code, which does not follow certain linearity properties, as we will discuss next, if we say take a 7-4 block code, you have to compute totally 120 distances, that is 16C2. This is 16C2 equals to 16 into 15 by 2, 120 distances between alternative pair of codes, and the pair of codes, alternative pair of codes you obtain by this 16C2, because you have 16 total different code words. 2 to the power 4 equals to 16, because you have got a 4-bit information vector. So in case of a nk value 1511, you have to compute how many? You see, 2048C2, that is 2048 into 2047 divided by 2, that is 1024 into 2047. So huge number of calculations you have to do. After this, again you have to compare between all these d values, that is the distance between code pair values, to obtain the value of d-min, which is the minimum of all these distances. Now this is a big job. In fact, if we go now for a linear block code, you will find that this task has become very easy, rather not much computationally intensive. What is that and how? Let us see in the next slide. First, let us understand what is the beauty of a block code, or rather linear block code. Definition of a linear block code is as such: a block code is said to be linear if its code words satisfy the condition that the sum of any two code words gives another code word. What is that? If you do modulo 2 sum bit by bit, you obtain the third code word from given two code words, for example C1 and C2, and we obtain C3 by doing the modulo 2 operations as shown, and we obtain 0 1 1 1 1 1 1 as the C3 or the third code word. Okay, this is very interesting, as we will see later, that in case of a block code which has certain linearity properties, this particular feature help us to obtain a very interesting feature of the block code that is given in the equation 4, that is DCI Cj, that is the distance between two code words I and j, is nothing but the weight of the code word ck, which is obtained by modulo 2 addition of ci and cj, which is the third code word ck. and this gives you the ultimate advantage in terms of evaluation of d mean, where d mean becomes now w mean, where w mean is the minimum of the weight of any non-zero code word with the in this entire code set. Fine. Now let us see how easy is the total number of computational requirements for such a beautiful property of a linear block code. For nk code, for 7/4 code for example, you have to now compute only 2 to the power 4, that is 16 values of code weights, and from there by comparison you get the minimum distance d mean. Okay, and in case of a 1511 it is just 2 to the power 11 or 2048 number of weight calculations that will finally lead to, after comparisons of 2 to the power 47 number of comparisons, it will lead to, or rather 2047 number of computations, it will lead to the formation of w, or rather d mean or w mean. Okay, now this value of d mean has got a impact or implication in terms of understanding what is the number of errors that the code can detect, or the number of errors the code can correct. That is, the error detection and correction potential of the code can be very well understood by obtaining the value of d mean. That is the beauty of d mean. Okay, the number of errors that the code can detect is I equals to d mean minus 1, or rather L equals to d mean minus 1, and the number of errors the code can correct is R, d mean minus 1 divided by 2. You can now do a very simple homework by taking the 7/4 linear block code, which for which the parity equations I have given. In fact, this very interestingly becomes a linear block code, as we'll see finally at a later stage of discussion in the class. Okay, and this, in this case you will find the d mean value equals to 3. Why this value equals to 3 is an interesting issue, and this can be studied in greater depth from the references. For example, reference 1. Okay, I have given 3 references, you can check any one of them. Reference 1 is a lecture note which will give you a very easy way of working and understanding the block code in a much greater depth. Fine. Now in this case, with the value of d equals to 3, you get naturally the value of L, that is the error bits that it can detect in a code word, equals to 2, and the number of error bits it can correct equals to R equals to 1. So this linear block code, 7/4 block code, will now have a error detection potential of 2 errors in the code word and 1 error in the code word. Fine. Here we end, and you please go through this entire video exercise or video discussion and the PowerPoint slideshow adjoining this to come up with the complete ideas, and then we will discuss in the class, from which you will understand in a much greater depth what and in how easy fashion you are to now calculate the value of d mean, and you can also obtain the code words and error correcting and detecting potential of a linear block code. In this case, we have given you an exercise for a 7/4 code. For any other code, 1511 code or any other code, you will be able to do it without any difficulty. Thank you all very much for giving a patient hearing.